Today we're going to continue learning about Lewis structures, and we'll start out by doing a little review. And as we do one of the practice problems, we'll notice that the rules that we learned before are incomplete, and we need to add to them to be able to draw Lewis structures for all kinds of molecules. And then we're going to look at how do we draw Lewis structures for polyatomic ions, because they're covalently bonded like molecules, so there must be a way to do it. Let's begin reviewing our rules for Lewis structures by doing the Lewis structure for carbon dioxide. Remember, how we start is we draw a dot notation for every atom that's in the compound, so we know how many valence electrons we have available. So I have carbon, which is group 4 and has 4 dots, and oxygen's group 6, so it would have 6 dots. But I have 2 oxygens. So 2 times 6 gives me 12, plus the 4 from carbon is going to add up to 16 electrons. So when my structure is all done, I should have 16 electrons in it. Next, I need a skeleton structure. We have a few guidelines for that. One is the closer an element is to the middle of the periodic table, the closer it's probably going to be to the middle of the molecule. So for carbon dioxide, that would put carbon in the center and oxygen on the outside. Now we know that carbon prefers to make 4 bonds, but it can't do that here because it's only bonded to 2 things. Next, we have to make sure that everything is stable. In other words, everything is a full octet. So one of the ways to do that is to think about every symbol in a Lewis structure as having 4 sides to it. On each of the sides, you have to have either a bond or a lone pair. For carbon, 2 of the sides have bonds, but 2 of the sides are empty, and so I put lone pairs on those 2 remaining sides. And for the 2 oxygens, only one of the sides is covered with a bond, and I need a pair of electrons on the remaining 3 sides. And that gives each of the atoms in this structure a full octet. And everything needs a full octet, remember, except for hydrogen. Just a bond is all it needs. Now, the last thing we're supposed to do is count the number of electrons in our structure, and if we've done it right, that's always matched the number of electrons that we had to start with. So that should be 16 in this case. If I count, here's what I find. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, which is far too many electrons. So what do you do? Well, if the structure has too many electrons, the first thing you want to do is remove a pair from each of 2 atoms that are bonded to each other. That'll drop your electron count by 4 because you've taken 2 electrons away from one atom and 2 more from another atom. And the second thing to do then is add a second bond between the atoms. Well, that puts 2 of the electrons back. So every time you do this process, you drop the electron count by 2. But you retain stability because you're filling that octet back up. Then count again, and if the structure still has too many electrons, you repeat this process. So going back to our CO2 example, we saw that we had 16 electrons that we were supposed to have in our structure. And this is the Lewis structure that we have so far, and it has too many electrons. So I'm going to find 2 atoms that are bonded to each other, like this left-hand oxygen and the carbon, for example. And I'm going to take a pair away from each of those, and I'm going to put a bond in between. So now I'll recount. 2, 4, 6, 8, 10, 12, 14, 16, 18. I still have too many electrons. So I'm going to do it again. Now, to keep things symmetrical, I'm going to take a pair from this oxygen and that remaining pair from that carbon, and I'll replace that with a bond. Now I'll do my count. 2, 4, 6, 8, 10, 12, 14, 16. Now I have the correct count. And the other thing that's interesting is I still have full octets, but now carbon is making its 4 bonds that it prefers to make. And so is oxygen making the preferred number of bonds. It's making 2, both of them are. Let's try another example, nitrogen. This is diatomic nitrogen, so it's got 2 nitrogen atoms. Nitrogen's in column 5, so that's 5 electrons for each, and that gives us a total of 10 electrons. Skeleton structure is a no-brainer here because there's only 2 atoms, so we stick them to each other. To fill octets, we notice that each of these nitrogens only has 1 pair of electrons, so we've got to fix that by putting 3 lone pairs on the remaining 3 sides of each nitrogen. Now when we count, we've got 2, 4, 6, 8, 10, 12, 14 electrons, which is too many. So remember what we do is take a lone pair from each of the 2 atoms away and then put in another bond. Recount. 2, 4, 6, 8, 10, 12. Well, it's getting better, but we're still not there, so I'll repeat the process by taking away another pair from each of the two nitrogens and putting another bond between them. Now when I count, I have 2, 4, 6, 8, 10. And that's the correct structure. Let me redraw just for clarity. It's a triple bond between the two nitrogens, and then each one has a lone pair. That means the nitrogens are sharing 3 pairs of electrons. So this is a pretty strong bond. And what that means is nitrogen is really stable. And that's good for us because our atmosphere is mostly nitrogen, so it's good that it's not blowing up all the time. You try this one. Follow these rules and draw the Lewis structure for HCN. Well, to start out with, I need to draw dot notation for each of the atoms that's in here. So I have a hydrogen with 1 dot, carbon's column 4, that's 4 dots, and then nitrogen's column 5, so that's 5 dots. When I add them up, I get 5 plus 4 plus 1, and that all adds up to 10 electrons. Skeleton structure. Well, I'm going to put carbon in the middle because it's closer to the middle of the table, and I want it to make as many bonds as possible, which looks like it's going to be only 2 to start out with here. Put nitrogen on the outside, and hydrogen has to be on the outside, so I'll put that on the other side of the carbon. Now, fill octets. Hydrogen doesn't need a full octet, but carbon and nitrogen do. That's going to require 2 lone pairs for carbon to have all of its 4 sides covered, and for nitrogen, 3 pairs. Now I'll count. I'm supposed to have 10 electrons. How many do I really have? 2, 4, 6, 8, 10, 12, 14 electrons. Too many. So the carbon and the nitrogen, I have to take away a pair from each of them and replace that with another bond. Recount. 2, 4, 6, 8, 10, 12. Still too many. So I repeat the process. Take another pair away from carbon and nitrogen and put another bond in between them. Now I count. 2 here, 4, 6, 8 with the 3 bonds, and then that hydrogen bond is the 10th. So that's the correct structure. For clarity, I'll redraw again. Triple bond between carbon and nitrogen, single bond to hydrogen, and that's my Lewis structure. Now, polyatomic ions are covalently bonded, and so we should be able to draw Lewis structures for them as well. We're going to find out that they have either missing or extra electrons because, of course, they're ions, and so we have to modify our procedure a little bit. So the first thing we do is draw the electron dot notation for each atom, just like you normally do. So you start out by doing what you would always do if you're drawing a Lewis structure. If the polyatomic ion is an anion, that means it has extra electrons. And so we deal with that by adding 1 electron for each unit of negative charge. So let's say we had this one, NO3 with a 1 minus charge. Because of that 1 minus, I would add 1 electron to the structure. Or say I had this one, SO4 with a 2 minus charge. I would add 2 electrons to my total count because apparently this ion has 2 extra electrons. So let's do an example. Hydroxide has an oxygen in it, 6 dots. Hydrogen, a single dot. So 6 here plus 1 gives me a total of 7 electrons. Here's a little clue. You'll never end up with an odd number if you've done everything right. So why is this odd? Well, here's what I have to deal with yet. This has an extra electron in it. So to compensate for that, I'm going to add 1 electron to my count, and that tells me I should have 8 electrons in my structure. Now, skeleton, very easy, only 2 atoms. Fill octets, hydrogen doesn't need 1. Oxygen needs 3 more lone pairs to have 8. Now I do my count. 2, 4, 6, 8. So that's the correct structure. Now later on we're going to find out that when we draw a polyatomic ions Lewis structure, we have to finish this thing off by putting square brackets around it like this and then installing a charge symbol up there. So that's the complete Lewis structure for hydroxide ion. If the polyatomic ion is a cation, that means it's missing electrons, and so we have to take electrons away from the count, 1 electron for each unit of positive charge. So for example, ammonium, NH4 1+. Let's draw the Lewis structure for this. It has a nitrogen in there, column 5, 5 dots. And 4 times it has a hydrogen in there with 1 dot. So this is 4 electrons plus 5 electrons. That gives me 9 electrons. Odd number, so something's obviously wrong, and here's what's wrong. I have to account for this. It's positively charged by 1, so that means it's missing a negative charge. It's missing an electron. So I'll subtract 1 electron, and that gives me a total of 8 electrons. So that's how many really belong in my structure. Now I do a skeleton. The hydrogens have to go on the outside, so that means the nitrogen has to be in the middle here. And nitrogen has a full octet already, because 4 bonds is 8 electrons. And now I do my electron count. Well, I already have sort of done that. 2, 4, 6, 8 electrons. So that structure is complete. Except, because it's an ion, I need square brackets and then install a charge. Try this one. Stop the video and give this your best shot. Follow the rules. See if you can come up with a Lewis structure for this, and I'll give you an answer in a minute. Okay, when I draw the dot notation, I have sulfur, which is a group 6 with 6 dots. And then I have 4 oxygens, also a group 6. So that means 6 dots. 4 times 6 is 24. And then 6 more for this sulfur. That all adds up to 30 electrons. But it's a 2- charged ion. So that means I'm going to add to my count 2 more electrons, and that'll give me 32 electrons in the structure. Sulfur is closer to the middle of the table. It's also the first thing listed in the compound's formula, so I'm going to put the sulfur in the middle and arrange the 4 O's around it. Sulfur has a full octet now, so I'm going to fill octets on the oxygens. Each one has only one side covered with a bond, so the other 3 sides get lone pairs. So 6 in lone pairs, and 1 in a bond makes 8 for each oxygen. So everything's stable now. I'm going to check my electron count. Each oxygen's got 2, 4, 6 in lone pairs. So among the 4 oxygens, then that means there'd be 24. Then with the bonds, 26, 28, 30, 32. So that's the correct number of electrons. Last thing I have to do, because this is an ion, put square brackets around the whole thing and install my 2- charge to get the Lewis structure. Here's another example. Try and do this one, and I'll give you the answer in a minute. Well, this has got nitrogen in it. Nitrogen's a column 5. That means 5 electrons. Oxygen is in there as well. Column 6, 6 electrons. And there's 3 oxygens. 3 times 6 is 18, so there's 18 electrons. Nitrogen gives me 5 electrons, so when I add these together, I get 23 electrons. Right away I know that I'm missing something, because I shouldn't have an odd number there, and what I'm missing is that extra electron that's in this polyatomic ion. So I'll add 1 more electron to account for that. That means my structure should have 24 electrons in it when I'm done. I'll put the nitrogen in the middle. I'll put the oxygens around it, because that's sort of what the formula is telling me to do, plus I know nitrogen wants to make 3 bonds, plus I know nitrogen's closer to the middle of the table. So for all these reasons, that's a good skeleton. Fill octets. Nitrogen's mostly okay, but it needs 1 more pair on its remaining unfilled side. Each of the oxygens needs 3 pairs for stability, and so I'll install those on the remaining 3 sides of that symbol. And now I'll do my electron count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have too many electrons in my structure. So the thing I have to do there is erase a pair from each of 2 bonded atoms and put another bond between the 2. It doesn't matter which of these oxygens I choose. I'll just go with the top one here. Take an electron pair away from both the nitrogen and the oxygen and put another pair in there. That should reduce my count by 2 and get me down to 24. Let's check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there's my correct structure. I'll redraw this to make it clearer, and square brackets and charge. One more. Cyanide ion. This is what they kill people with in the gas chamber. CN1-. Give it a try. I'll give you an answer in a second. Okay, as usual, we have to start out by drawing the dot notation for every atom that's in here. So that's 1 carbon and 1 nitrogen. That's all that's here. So that's 5 dots plus 4 dots. That means 9 valence electrons will be in my structure. But it's a 1- ion, so that means I'm going to add 1 more electron to my total, and that gives me a 10 electron count. So my structure will have 10 electrons when I'm done. It's 2 atoms, so a very simple skeleton structure. Fill octets. Carbon gets 3 more pairs. So does nitrogen. And when I count 2, 4, 6, 8, 10, 12, 14, I have way too many electrons. So I'll take away a pair from each of the two atoms, put another bond in there. 2, 4, 6, 8, 10, 12 is now my count. Still too many, so I do it again. And I end up with a triple bond. Counting again, 2, 4, 6, 8, 10 electrons. So this is right. Now the thing we have to do to finish this off is square brackets and a charge.